Hi everyone, I am Manzoor Mohammed, Assistant Professor of CSE AML of Bardhaman Engineering College. In this video, we are going to discuss about bitwise operators and bit manipulations. So how they are going to useful in problem solving. Okay, so bitwise operators can be used to solve complex problems with a simple code. So in this video, we'll discuss about what are the bitwise operators available in different programming languages and how they can be used to solve problems. Okay, bitwise operators. As the name suggesting, bitwise operations are performed at binary level or bit level. So when you are writing number and you are using bitwise operators, the operation going to be performed at bit level, not at decimal level. So whatever the numbers we are writing, like 253 or 126 or 17 or 1 or 0, all these are least in numbers, that means decimal numbers. But when you perform bitwise operations, the operations are going to be performed in binary level. Okay, so what is binary level? Binary number. Okay, so binary numbers uses only 1 and 0 in the representation. So in decimal, what we are using? We are using the digits in the starting from 0 to 9. So we can use digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, all these digits to make it number. But when you are writing a binary format, to construct a number, you are allowed to use only these two digits. Either you have to use 1 or you have to use 0. So what is 1? What is 0? It's simply 1 means you are including a 2 power at particular position. 0 means you are not including 2 power at particular position. So what is that? So I'll write an example binary representation. Okay. So suppose let us take a random number. Suppose 73. This is a decimal number. Now I want to convert it into binary format. So you can do this in two ways. First way is the simplest way. 73. You have to do LCM with 2. So 2 3 is 6. 2 6 is 12. You have 1 as remainder. Then 2 8 is 36. 0 is remainder. Then 2 9. 0 is remainder. Then 2 4 8. 1 is remainder. Then 2 2 4 0 is remainder. Then 2 1 2 0 is remainder. Now the binary format we will go in this direction. So the binary number becomes 1 0 0 1 0 0 1. What it means? What is it is telling to us? Okay. So to understand that, there is another simple way to represent a binary number for particular decimal value. What is that? Assume that you went to a departmental store. Okay, you went to a departmental store and you want to purchase 73 kg of rice. Okay, you are purchasing 73 kg of rice. Okay, assume that there is no digital weighing machine. You have a manual mechanical weighing machine is there. So then the only weights are available is there is 1 kg weight, 2 kg weight, 4 kg weight, 8 kg weight, 16 kg weight, 32 kg weight, 64 kg weight, 128 kg weight. Okay, so assume that we have these weights only available. Now I want purchase 73 kg of rice. Now what the shopkeeper will do? So he will have two basins inside. So in one basin they will keep the weights, another basin they will keep the rice. Okay. So how I can make 73 kgs? So first he will try to include less number of weights. So When he will start, first he will get 64 kg weight. Okay, he will give 64 kg weight. So when you are including that weight, you assume you are keeping 1. Now 64. Now, if I add 32 kg weight to it, what happens? It will exceed 73. So, we won't include it. Now, 64 plus 16. That is also exceeding 73. So, keep a 0. 64 plus 8. How much it will become? 72. So, which is less than 73. So, I'll keep 1 here. Then, 72 plus 4, it will exceed 73. 72 plus 2, 72 plus 2, 74. That also exceeds 73. So, I'll keep 0. Sorry, this is also 0. 64 plus 8, 72. 72 plus 4 exceeds. 72 plus 2 also exceeds. Now, 72 plus 1, 73. So, 1. So, that is exactly 73. So, what we got? We kept 64. We kept 8. We kept 1. And we are not considering 32. We are not considering 16. We are not considering 4 and 2 also. So, then what is the value we are getting? 1, 0, 0. 1, 0, 0, 1. Which is same as this. Whatever we get. So, what they are telling? Your number is constructed using this. What is 1? 2 power 0. What is 2? 2 power 1. What is 4? 2 power 2. What is 8? 2 power 3. 16 2 power 4. 32 2 power 5. 64 2 power 6. And 128 2 power 7. And so on. So, what is this representation telling us? Okay, you include 2 power 0 in your value. Plus, don't include 2 power 1. So, 2 power 1 into 0. Okay. Next. 2 power 2 don't include. So, 2 power 2 into 0 plus you include 2 power 3. So, 2 power 3 into 1 plus you don't include 2 power 4. So, 0. You don't include 2 power 5. So, 0. You include 2 power 6. So, into 1. Now, what will get? 2 power 6 is 64 plus we are not including 32, we are not including 16, we are including 2 power 3, we are including. So, 8 plus we are not including 4, we are not including 2, we are including 1. So, 1. So, what it is summing up to? 73. So, these ways you can use, but if you are very good, if you remembered all the 2 powers, you can easily write for any number binary format. So, by the practice, you can on the go write the binary formats. Okay, if you are very clear with all these binary formats. Now I hope you understood how to write a binary format for given a decimal number. Okay, now we'll discuss about binary operators available in programming languages. Right? Now, the binary operators are bitwise operators which are available in almost all programming languages, starting with AND operator, OR operator, we use pipe symbol, XOR operator, we use cap symbol, NOT operator, okay, NOT operator, we use tilde symbol, shift left, shift right. Okay, these are the operators we are going to use in bitwise operations. Now we'll see one after another. Okay, now assume that, first we'll go with AND operation. AND operation, as the name suggests, is AND. So, you need both inputs. Whatever you are applying with AND operator need to be 1. Then only you will get 1. Okay. If both inputs are 1, then only you will get the result as 1. Remaining all cases, that is, if any one of the bit is 0, you will get the outcome as 0. For example, I am giving 2 inputs. Okay. One and 1, you will get the outcome as 1. Okay. So what is the operation we are doing? AND operation. Otherwise, if one bit is 1, other bit is 0, you will get with AND operation result as 0. In inverse of this, one input is 0. Inverse of this, suppose if one bit is 0, another bit is 1, okay, and we are applying AND operation, then also we will get 0. And finally, if both inputs are zeros and you are applying AND operation, then also you will get 0. Suppose simply you remember, suppose to a person, a doctor said, you take medicine and you take food. If you apply these two, then only you will be healthy. Doctor is saying, you take medicine and you take food, then only you will be healthy. If any one is missing, you will become ill. Okay, you will become ill. Patient taking medicine, patient taking food. Suppose if we represent with 1, the person will be healthy. Patient not taking medicine, but is taking food, so he will fall ill. So this case leads to here. Patient is taking medicine, but not taking food, then also he will fall ill. Patient neither taking medicine, nor taking food, so in both cases, again he will fall ill. So that is AND operation. So you need to take both of them. Okay, you need to have both inputs as 1, then only you will get result as 1. That is AND operation. OR operation. For doing OR operation, we use a pipe symbol. So for this, the only condition is if any of the bit is 1, your outcome will become 1. If both inputs are zeros, then only you will get outcome as 0. If and only if your both inputs are 0, then only you will get the outcome as 0. Now 1, 1, you are applying OR operation, you will get the outcome as 1, 1, 0. Okay, OR operation, you will get 1. So OR, you are saying OR, either you take this or you take that, both will be fine. Okay, and your input is 1, input is 0, another input is 1, and you are applying OR operation, you will get 1. But if your both inputs are zeros, if though you are applying OR operation, your output will become 0. Now let us take same example. Doctor is saying, you take food or you take fruits, be healthy. The patient, either he can take food or he can take fruits. Okay, normal rice are also he can eat, or he can eat fruits. Now in the first case, he is taking food, he is taking fruits. Okay, fine, patient will be healthy, so we'll get outcome as 1. Now patient taking only food, he is not taking fruits, that is also fine, still he can be healthy, so we'll get 1. Patient not taking food, okay, patient not taking food but taking fruits, that is also fine, we'll get 1. Now the last case, patient neither taking food nor taking fruits, so he will feel hungry and he will fall ill, so 0. So that is OR operation. If you take any one thing, that is sufficient. If any of the input is 1, then you will get the outcome is 1. Or if your both inputs are 1, then also you will get 1. But if your both inputs are zeros, you will get outcome as 0. That is OR operation. XOR operation. XOR operation. Exclusive OR. This is exclusive OR. What is meaning of exclusive? Specifically. So when you are getting both inputs, either this need to be 1 or exclusive OR, this need to be 1. So if you have this one, you should not have this, or if you have this, you should not have this, then only your outcome will be 1. That means 1 0, specially OR, only one thing you have to take, you will get 1, or 0 XOR 1, you will get 1. If you give both of them, you will get 0. If you are not giving both of them, you will get 0. So again we'll take another example. Suppose there is a powerful tablet is there, patient is ill, doctor asks you take this powerful medicine. Now there are two brands which are uh, making this drug. Okay, so tablet. Suppose company A, company B, same tablet, but they are very powerful. You have to take only one tablet, either from company A or company B. Now patient purchased this one, okay, not purchased this one, so he is not taking this. You will get with XOR operation, you will get outcome 1. Fine. Patient not purchasing this, patient taking this and is consuming that, so XOR, you will get 1. Fine. But patient purchased A, purchased B, both tablets he is taking at a time. So with a overdose, patient will fall ill, 0. Patient neither purchasing this A nor purchasing B, so he is not taking anything, still patient will fall ill, so 0. So exclusive OR, so you need to have only one bit as active, set bit 1, other bit need to be 0. Then only you will get 1 as outcome. This is XOR operation. NOT operation. In NOT operation, simply it will invert the bits. That means if your bit is 1, it will be made as 0. If your bit is 0, it will be made as 1. For example, I'll take a number 17. Okay, 17 binary format 16 plus 1. So 16, there is a 16, there is no 8, there is no 4, there is no 2, there is a 1. 16 plus 1 is 17. This is binary format of 17. Now when you apply negotiation to 17, what happens? Every bit will become opposite. Okay, so if you have 1, you will get 0. If you have 0, you will get 1. So 1 will be made as 0, 0 will be made as 1, 1, 1 and 0. Now what is its value? For a human eye, it is looking like 8 plus 4 plus 2. That is 14. Okay, but it is not 14. It is not 14. Okay, but negotiation of 17 is minus 18. That is, whenever you do negotiation, you are doing 1's complement. Okay, you are doing 1's complement. That is, okay, inverting each and every bit. What is 1's complement, sir? So, for understanding that, so please observe, we are writing binary format in, okay, 2's powers. Now, how many 2's powers will be there in a particular given number? For an integer number, for example, if you are talking about integer number, there are total 32 bits. There are total 32 bits. That means starting with 2 power 0, ending with 2 power 31. Ending with 2 power 31. Okay. Now, this is called as most significant bit and this is called as least significant bit. Okay. Now, please remember the value of most significant bit, as we discussed, 2 power 31, but in reality it is a sign bit and the value is, it's not 2 power 31, it's minus 2 power 31. Minus 2 power 31. So when you have a set bit there, that is 1. Okay, when you have a set bit there 1, that means you are including minus 2 power 31. So your entire value will become the negative. Your entire value will become negative. Okay, so with this we can draw one more point to here. So to get the maximum value, that is, I should have 0 here and remaining all ones. So what it is equivalent? 2 power 31 minus 1. 2 power 31 minus 1 is the maximum value we can get. Okay, now coming to our discussion. So 17 is a positive value. So left side of this we have all zeros and including this MSB bit also. Assume that this is my 2 power 31 bit. Okay, minus 2 power 31 bit. So this is also 0. Of course, we have more zeros in between, but assume that this is minus 2 power 31 and 17 is a positive number, so we have 0. Now, when I invert the case, using NOT operation, this will become 1. So at this position, the value is, actually we should have a 32 here, okay, but this will become 1, this also becomes 1, 1, and so on, 1. So what it becomes? It will become minus 32. Instead of positive 32, till here the sum will become plus 32. So how plus 32? Simple calculation. Minus 2 power 31 plus 2 power 30, because we have a 1 here. Minus 2 power 31 plus 2 power 30 is minus 2 power 30. Minus 2 power 30 plus 2 power 29 minus 2 power 29. Similar to that, and so on when we continue this summation. Okay, so this is 2 power 5 minus 2 power 6 plus 2 power 5. Minus 2 power 6 plus 2 power 5, it will become minus 2 power 5. So we have a minus 32 here. So till here we have minus 32. Okay, so minus 32, because we have 1 here, minus 32 plus this is 16, this is 8, 4, 2, 1. Now we have 0, so we won't include 16. Minus 32 plus 8, we have 1 here, so minus 32 plus 8 is 24. Minus 24, in fact, minus 24. Till here we have minus 24. Minus 24 plus 4, minus 20. Minus 20 plus 2, minus 18. Minus 18 plus 0, minus 18. Okay, so the value is minus 18. That's why it is became negative value, because we have 0 there, because it is a positive number, but when we apply NOT operation, that will become 1, so it will become a negative value. So if we have a negative number, there will be 1. When we apply NOT operation, that will become 0, so positive number. So easy to write NOT operation value. So if your value is x, when you are applying NOT operation, the outcome will be minus of, okay, multiply with minus operator, because minus, if you are already minus into minus, it will become plus. So when you apply negotiation operation on x, you have to simply doing minus of x plus 1, minus of x plus 1, that is negotiation of 17 will become minus of 17 plus 1, 18, so minus 18. Okay, negotiation of 38, okay, it will become minus 39. So negotiation of minus 47, it will become, so 47 minus 47 plus 1, so minus 47 plus 1 will become minus 46. Further apply, multiply with again minus 1, so it will become minus into minus plus 46. Okay, so this is all about NOT operation. Okay, I hope you understood this NOT operation. Now we'll move to the final two operators, which are complement to each other. Okay, shift left and shift right operator. Okay, shift left and shift right operator. Shift, and this is shift left. Okay, shift left operation. In shift left operation, we use double less than symbol. Okay, now suppose I have a number, let us take 13. Okay, 13. Now what is the binary format of 13? So 13 is 8 plus 4 plus 1. 8 plus 4 plus 1. 1101. Okay, now for understanding, I am adding 4 more zeros to it. So okay, now I have positions like this. Now when I apply shift left operation, suppose I am doing shift left by 1 position. 13 shift left by 1 position. So every bit will move towards left side. Every bit will move towards left side in shift left operation. So this 1 will be joined here. The 0 comes here. The 1 comes here. This 1 comes here. The 0 comes here. The 0 comes here. And the 0 comes here. And subsequently, because there are 32 bits for an integer, same thing will be done. Okay. Now whatever overflow bit, so the extra bit is there, that is discarded, and this will be replaced with 0. Now what is this value? Now this is 16 plus 8 plus 2. So that will become 26. You can observe that, which is, okay, so multiplied by 2. Okay, so 13 into 2. The value which you are using for shift left operation, okay, will be multiplied by 2. Okay, for one position. If I do 2 positions shift left, okay, now 2 positions we are moving. For example, this one will be joined here, 0 will be joined here, 1 1 0 0. Now instead of 1, 2 bits will be discarded and 2 bits will be replaced with 0. Now what is this value becomes? 52. How 52? 32 plus 16 plus 4. Okay, so 16 plus 4 20, 20 plus 32 52. So the value became 52. That means when you are shifting left side towards 2 positions, it is 13 into 2 positions, so 2 power 2. Here 2 power 1. So if you are shifting x by y positions, it is nothing but x into 2 power y. X into 2 power y. Okay, x into 2 power y. That is shifting left operation. Simply you are moving left side. That means all are 2 positions only. Every position is associated with 2 power. So 2 power 3 will become 2 power 4. 2 power 5 will become 2 power 6. 2 power 10 will become 2 power 11. So there is an improvement of or increasing of 2 multiplied by 2. Every bit is moved towards left side. So every value is upgraded into 2. So that is shift left operation. Now shift right operation completely opposite. So when you are moving left side, you are improving 2 power. So when you are moving right side, you are decreasing 2 power, because 2 power 3, 2 power 2, 2 power 1. So values are decreasing. So instead of improvement, the values will be divided by 2. Here value is multiplied by 2 when we are doing shift left. When you are doing right shift, the value will be divided by 2. For example, shift right side. Okay, now let us take a number 17. 17 is 6. We'll take different number. For example, 14. 14 is 8 plus 4 plus 2. 8 plus 4 plus 2. Okay, this is 14. Now 14 right shift by 1 position. Okay, now right shift. So this one will be joined here. So this one will be joined here. This one will be joined here. And this is 0. This is discarded. Now what is this value? This is 7, which is nothing but 14 by 2 power 1. 2 power 1. Now further if I right shift by one more position. So 14 right shift 2 times. So now this one will be moved to this position, because 2 positions. First position, second. Okay, sorry. This is initial position. This is first shift. From here, second shift. So one comes here and another one will be joined here, and these are replaced by zeros, and these two only considered. This and this both will be discarded. Okay, now what is this value? It is 3, which is nothing but 7 by 2. Okay, 7 by 2 is 3.5, but we will take only integer part. So when we do right shift by 2 positions, it is 14 by 2 power 2. Now what is the conclusion we can draw? When you are right shifting x by y times, it is same as x by 2 power y. What about left shift? Again, x left shift y times means x into 2 power y. Okay, x into 2 power y. This is left shift operation. So finally there are different operators, bitwise operators available, and operation in when both inputs are 1, then only you will get 1. In all remaining cases you will get 0. In OR operation,
If any of the bit is 1, you will get outcome as 1. If both bits are zeros, you will get outcome as 0. Exclusive OR, when you have different bits, then only you will get 1. If you have same bits, either they can be 2 ones or 2 zeros, you will get outcome as 0. Negotiation operation or NOT operation, all the bits are inverted. That means if you have 1, it will be made as 0. If you have 0, it will be made as 1. And it is a unary operator. Remember this. It is a unary operator. That means you can apply only one operand, one value to it. Okay. Next, shift left. Your values are, bit positions are moved towards left side by specified number of positions, and that is nothing but multiplying by 2. And right shift, your bit positions are moved towards right side, that is divided by 2. Okay, this is all about bitwise operators. Using these operators, we can solve many problems. We are going to see them in our coming videos. Okay, thank you.